Okay, Unit 6 test, Part 2. This is no calculator. So let's take a look at number 8. And they tell us the integral from 0 to 3 is 6, and the integral from 3 to 5 is 4. And now they're asking us to find out what this is. So when I go through, and I'm going to rewrite this. So from 0 to 5 of 3 dx plus the integral of 0 to 5, and I'm going to factor out this 2, of f of x dx. And I know from 0 to 3 is 6, and from 3 to 5 is 4. So I know from 0 to 5 must be those two put together. So that's 6 plus 4 is 10. And now I'm going to go through and take the antiderivative, do the integral, and use the fundamental theorem of calculus. So this is 3x over 1, evaluated from 0 to 5. So we put in the 5 first. So it's 15 minus 0 plus 20. Hey, that's going to end up being 35. All right. Well, I didn't see it for a second. So number 8 is D. And this is Form A, although I gave you all the same form. Okay, so for number 12, hey, we have g of x equals x squared minus 3x plus 4, and then f of x equals g prime of x. So then the integral of 1 to 3 equals f of x dx. So let's look at what I have here. So first of all, they tell us what g of x is. And then they say, okay, f of x, not the derivative, f of x is the derivative of this, so that's 2x minus 3. And so now what they're asking me to do is, hey, take the integral from 1 to 3 of 2x minus 3 dx. So I am going to get 2x squared over 2 minus 3x. I'm going to evaluate that from 1 to 3. Those 2's are going to cancel out. So I'm left with x squared minus 3x evaluated from 1 to 3. And the fundamental theorem of calculus says put the 3 in first. So that's 9 minus 9. Those are gone. And then subtract when I put the 1 in. 1 squared is 1. Minus 3 times 1 is 3. 9 minus 9 is 0. Minus a negative 2, which is just going to be equal to 2. So number 9 is C. Okay, so we just had to do a little bit, take the derivative of what they gave us, and then use that as our f of x. Okay, so again, no calculator. Just got to follow step by step. Don't get too caught up. Okay, given to the right is the graph of the derivative. Okay, if f of 0 equals 9, what is the value of f of 2? All right, right now, I like to think of this as they are talking about the derivative, but they ask us to find something with the original function. So whenever they do that, I'm going to use the fundamental theorem of calculus, and the integral from 0 to 2 is equal to the antiderivative f of 2 minus f of 0. Okay, I am trying to find this. They give me f of 0. They told me that was 9. And then this right here is the area under the curve. Okay, because it is of the graph of the derivative, and the integral is the area under the curve. So from 0 to 2, that's just here. I get this little rectangle and a quarter circle. So the area under the curve is equal to, this is 2 times 1 is 2, plus 1/4 pi r squared, and the radius is 2, which will be 4, which will be 1/4 times 4 is 1. So this is 2 plus pi. That's not our final answer. They didn't trick us with that. But this is equal to f of 2, I don't know, minus f of 0, they gave that to us as 9. So when I add 9 to both sides, 2 plus 9 is 11. 11 plus pi is equal to f of 2. And we love it when we do our work, our solution shows up. So number 10 is E. Again, fundamental theorem of calculus, understanding that the integral of something is the area between the curve and the x-axis. Fundamental theorem of calculus, just we evaluate the integral from the upper limit of the interval minus the lower limit of the interval. So that's good. Okay, number 11. A left-hand Riemann sum, a right Riemann sum, and a trapezoidal sum are used to approximate this value from 0 to 1 of fx dx, and this is the graph of f of x, each using the same number of subintervals. The graph of the function is shown in the figure to the right, which of the sum gives an underestimate of the value. So if I do left-hand sum, that's going to be this, 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 so on and so forth. So left-hand sum's an under estimate or under approximation. Right-hand Riemann sums, right now I should see, hey, these are all going to be over. So that doesn't work. And now trapezoidal sum, let's do this in yellow. I'm going from here to here. Hey, that's going to be under. Then I go there to there, that's under. There to there, that's under. Okay, so that works. So 1 and 3 work. The answer is D. Okay, so don't be afraid. And if I sketch it and I can't tell, then I can just re-sketch the problem. Okay, the function's going like this. Oops, sorry, my trapezoid would be under always. Okay, good problem. Number 12, a tank contains 50 liters of oil at time equals 4 hours. Oil is being pumped into the tank at a rate of R of T, where R of T is measured in liters per hour and T is measured in hours. Selected values of R of T are given in the table above using the right Riemann sum with 3 subintervals and data from the table. What is the approximation of number of liters of oil that are in the tank at time equals 15 hours? They gave us which kind of Riemann sum and how many. So right Riemann sum, 3 subintervals. So I'm going to do these 2, that's 1. These 2, that's a second. These 2, that's a third. So it's just Riemann sum, area of rectangles, and I add them all up. So 4 to 7 is 3, and then I use the right-hand value, that's 6.2. 7 to 12 is 5. Use the right-hand value, 5.9. 12 to 15 is 3. Right-hand value is 5.6. And I do these out, 18.6. That should be 29.5. 16.8, and we should get this right here, 114. No, that can't be right. Okay, yep, I didn't add the 50. So mine will add up 18 and 29 is 37, 63.8, 64.3, 64.9. So mine adds up to 64.9, but then I had 50 liters of oil in it. So I got to do the plus 50 and I get my 114.9. Okay. Again, that's like the second or third problem I would have got wrong just by being in a rush and not paying attention to what initial amount was in there. Okay. Number 13, the function f is continuous on a closed interval from 0 to 6 and has the values given in the table above. The trapezoidal approximation from 0 to 6 found with 3 subintervals of equal length is 52. What is the value of k? Okay, 3 subintervals. Now, the nice thing is they gave us equal subintervals. So I'm going to kind of do this a shortcut way, 1/2 times 2. And now we use our first interval once. Our first base once, our second base twice, third base twice, 2 times 8, and our last base once. And this whole thing is going to be equal to 52. And now let's solve it. 2 times 8 is 16, plus 4 is 20, plus 12 is 32. That's 1. So, oh, wait, I just said 32. Excuse me. 32 plus 2k equals 52. Subtract 32 from each side. We get 2k equals 20. K equals 10. That's one of our choices. The answer is D. Okay, so just use what we know about Riemann sums and trapezoid. Because those were all the same intervals, that's where I can do 1/2 the height and then all the bases. And again, the bases at the end are only used once, and all the bases in the middle are all used twice. That's why I had 2 times k and 2 times 8. Okay, last multiple choice on part 2. Use the table of values below to answer question 14. F of x is a twice differentiable function for which the values f prime, and f double prime are given. So I just give you that twice differentiable to say there's no tricks here. Let's just see what we can get. Okay, find the value here. So I'm going to break this up using the properties of integrals. And let me just do it the long way first. So the integral of a sum is the sum of 2 integrals. So this would be the first thing we would do. And I'm going -3 to 1. Don't forget that. Okay, so I would do this. And now, let me just write one more step. I'm going to take out the constants. 2 of f prime of x dx plus, let's put the 3 here, the integral from -3 to 1 of f double prime x dx. Okay, so now this is going to become, what's the integral of the derivative? That's just the function. And that's going to be f of 1 using the fundamental theorem of calculus. So I'm skipping a step here. So I'll use my data table to do that. And now I'm going to do plus 3 times, what's the integral of the second derivative? It's the first derivative, but I'm going to use the fundamental theorem of calculus to get this. And now I just use my table. So I'm going to put these values up here. 2 times f of 1 is 7. 7 minus f of -3 is 7. 7 minus 7 is 0. So 2 times 0 is going to be gone. Plus f prime of 1 is 5. And then f prime of -3 is -5. And so now I get 5 minus -5 is going to be positive 10. That's 0. 3 times 10 is 30. And that's our answer. Okay? So a lot going on there. It's not as complicated as it looks when you first read the problem, but you just need to break it up using the properties of integrals. Okay, let's go to the free response here for part 2. No calculator. Particle's moving along a straight path. The velocity of the particle from time to 0 to 30 shown in the table below. And velocity is at a maximum at time equals 20 seconds. Okay, so it hits its maximum somewhere in here. Answer the questions followed. Using midpoints of 5 subintervals of each length from 0 to 30, approximate the value of 1/30th 0 to 30. So I have to go through and I got to use the 5 subintervals. So it looks like I'm doing 3 of them. There's 1, there's 2, there's 3, there's 4, there's 5. Now, the nice thing is 0 to 6, 6 to 12, 12 to 18, 18 to 24, 24 to 30. So they're all going to be 6. And then I'm using the midpoints for all these. So 7.5 is a height, 12.5 is a height, 13.5 is a height, 14 is a height, and 13 is a height. So the problem is this is going to give me the area under the curve. This 1/30th means what's the average value. So at the very end, I have to then multiply by 1/30th or divide by 30. Okay. So this is asking for the average velocity during the first 30 seconds. And that's one of the questions they ask. Okay. And that would probably be worth a point. Average velocity of first 30 seconds. Okay. But now let's go through and find that answer. 7.5 and 12.5 is 20. 47, 60.5 times 6. Oh, that's just 1/5. Oh, that's kind of nice. That's going to go 12.1. And I know that's not necessarily just in meters, because that's what I would get if I added them all up. But then by dividing by that 30, I'm bringing in the time, so it's meters per second. Okay, so this is the average velocity over the first 30 seconds. Okay, and a point would be that meters per second. Okay, find the average acceleration. So average acceleration between 6 and 18. This is talking about velocity. So average acceleration is just the slope of the secant line. So I'm going to do average acceleration equals the value of the velocity at 18 minus the velocity at 6, and then 18 minus 6. I'm going to go back to my data tables and look at these points. 14.1 minus 10.1 all over 12. 4/12, which is 1/3. We'll just leave it as a fraction. 1/3, and it's acceleration. So I want meters per second squared. Okay, 1/3 meters per second squared. Good, and that was worth 1 point. Okay, and now find an approximation for the derivative at 6. Well, remember, even though there's a 6 here, an approximation, I'm going to use the value a little bit below it and a little bit above it. So now v prime of 6 is going to be equal to, and approximately equal to, let's do a little bit above first, v9 minus v3 all over 9 minus 3. So we're using the slope of the secant line as an approximation for the slope of the tangent line. And this is going to be 12.5 minus 7.5 all over 6. And this ends up being 5 over 6. And once again, this is an approximation of the derivative of velocity, which is acceleration. So it's going to be meters per second squared. Okay, and if they did that, if you did it as a decimal, it's like 0.833333 meters per second squared. And what is this? This is an approximation of acceleration. Acceleration at time equals 6. And is the speed increasing or decreasing? So, hey, I knew the velocity. If I look on the front page, again, hey, the velocity at 6 is positive, and I'm just finding that the acceleration is positive. So now I know speed is increasing. Again, why? Because velocity is positive and acceleration is positive. And again, remember, acceleration is the derivative of velocity. All right, so since they have the same sign, speed is increasing. Okay, last part here. During what interval of time is acceleration always negative? And so this negative acceleration is going to occur from 20 seconds to 30 seconds. And let's go back and look why. So from 20 seconds to 30 seconds, this is the only time it reached its maximum at 20, and then it's going to be decreasing the whole way there. Okay? So why is that true? Because the velocity is decreasing on the interval. Okay, so hopefully this was helpful. Continue working on your notes for, we'll say interval. Oh my goodness, man. My thing is dying. Good thing it's almost the end of school. So just keep working on Unit 7 notes, Unit 7 homework. We'll do the same thing next Sunday for the Unit 7 assessments. I'm hoping you had a chance to look at these first. But either way, hopefully that should solidify some of the stuff we did in Unit 6 and what you're expected to be able to do on the test. Okay. We'll go over any questions in class.